Okay, welcome to lecture here. We get started in just a bit. We just got just a smidge to go in the last chapter here, just to finish up the last little bit. So like I said, we don't have very much to go, but we'll just finish this last little topic, maybe review what we talked about here last week to finish up on. Okay, so we been talking about kinetics here, and like I said, we pretty much have finished the chapter, just one small bit to talk about. But last time we kind of got into the idea of the effect of temperature on the rate. So we continue to talk about sort of the relationship, the Uranus equation. We saw sort of the graphical version of it, like we talked about last time, where again, you could use the rate constant. You could also use 1 over the temperature in Kelvin and make a plot. And from that plot, you can graphically determine things like the activation energy, which again, the activation energy is that sort of minimum amount of energy that's needed for a reaction to occur. As we've seen in some of those diagrams, it's sort of the hill, again, that they have to climb to get to the other side. Obviously, that's going to affect the rate. The larger that hill, kind of the slower the reaction you would expect to occur, as opposed to if you had a reaction where the activation energy or that hill was relatively small, you would expect that reaction to probably proceed a lot quicker. Now, we also saw sort of a sometimes referred to as 2-point version, a more calculation-based version of that equation, where as long as you have sort of 2 pieces of information at different temperatures, you could kind of plug into that one. And that was the natural log of K2 over K1 equals E of A over R, 1 over T1 minus 1 over T2. Again, both of those temperatures in Kelvin. We also talked about the importance of units when you're using that equation. Again, R being that 8.314 joules, while activation energy is typically given in kilojoules. So definitely if you're given activation energy and you're using R, you do want to make sure, again, you're in the same units. You could go either way really on that. You could go kilojoules or you could convert them to joules. In general, when you solve for something like activation energy, it typically is in kilojoules. So that's the typical units that you get. And usually it is a positive number, sort of as you can see on the graph, that positive hill in terms of energy that they have to climb to get to the other side. Remember that, you really do need sort of 2 things to occur when a reaction happens. You do need a sort of a collision to occur. It does need to occur in sort of the right location, and does need to have that sort of minimum amount of energy for everybody to break apart. Again, not all collisions will result in actual products being made if those sort of 2 factors don't basically occur. Why temperatures usually will increase sort of the rate of the reaction is just for that sort of reason, that activation energy hill, obviously. If you increase the temperature, you are going to most likely get a greater number of or proportion of molecules that have sufficient energy to really get up and over to the other side, as opposed to a lower temperature. Everybody would have a little less energy, would have a smaller proportion that can actually have enough to get to the other side. Thus, we would see a slower rate there in the lower temperature. And we saw that, I think, in the experiment last week. The one that he put on ice was the slowest. The one that was in the warm water bath was sort of the hottest in terms of temperature, also has sort of the fastest rate. And then obviously the sort of room temperature in between those two has sort of I'll call it the medium rate there, that fell between those two. So we've also talked about the idea that, in a sense, if you raise the temperature about 10 degrees Celsius, you could pretty much kind of double the rate of a reaction in most cases, or a lot of cases, and that will usually speed it up. Then we sort of got to the end here of this chapter, and we really started talking about the idea of mechanisms. And mechanisms, again, are really sort of tentative explanations for how a reaction may proceed. Does not necessarily mean that 100% of the time it may always proceed in this fashion, but a lot of reactions do not necessarily occur like in a one-step fashion, even though we sort of think about it that way, because most of the time we're dealing with the overall reaction, but not all reactions really just go directly from reactants to products. There may be 2 steps, 3 steps, a whole bunch of steps sort of along the way that gets you to the overall reaction and to the sort of those products being made. An example of that, as we saw earlier on here, was the idea of, excuse me, the NO plus the O2 making NO2. Again, a product such as, or a molecule such as N2O2 was sort of seen being detected in that reaction. But when you look at the overall reaction of NO plus O2 goes to NO2, there's no N2O2 present. And that would imply that it was made early on and then kind of used up. And that is what we call sort of in a mechanism an intermediate. And an intermediate, again, is some type of molecule or substance that gets made in an earlier step in the mechanism, but by the time the mechanism is completely done, it is used up. So we don't see intermediates in the overall reaction, and that's why on another example that we did, we had something that sort of canceled out but didn't completely cancel out, sort of reduced down. I think it was like NO or NO2 or something like that. And the idea there was that it was still there in the overall reaction, which means even though we sort of reduced it down, we didn't completely get rid of it, which means it's not an intermediate in that particular case. So reactions can occur in these sort of mechanism sort of approaches, which are individual steps, which are sometimes referred to as elementary steps. And these elementary steps basically should lead to your product being made. Now, when we look at sort of a mechanisms, there's usually a step that's referred to as the rate determining step, or the RDS. And the rate determining step is the slow step in the mechanism. It is really the step in the mechanism that really determines the overall rate for that particular reaction. Because as soon as that step's sort of over, the rest of the mechanism could sort of proceed, or the rest of the reactions could sort of proceed relatively quickly. So when we look at a mechanism and trying to determine whether or not it's sort of a good mechanism or a bad mechanism, there's really 2 major things that need to happen when you look at the mechanism. The first one is a very simple one. If you take all the steps that are in a possible mechanism, they do need to add up to the overall reaction that you're looking for. So obviously, if you just add together all the steps of a mechanism and you don't get the overall reaction, it's not a good mechanism. Secondly, if you do add up all the steps and everything's good in terms of that, everything meets the overall reaction or equals the overall reaction. The second thing that should happen is that the rate law for the slowest step in the mechanism should match the one that has been found experimentally. So in a lot of sort of mechanism problems, they will give you the experimentally or observed rate law for a particular mechanism. And when you write the rate law for the slow step, or the RDS, it should match that one. And if they do match, then you're good to go. It's a good mechanism. Or if it's not really a question about is it a good mechanism, but they want you to determine, you know, which one is the, what is the rate law, you would write the rate law for the slow step, and that would be technically the rate law for the overall reaction as well. Now, there's a couple ways you can figure out this rate determining step. Like I said, probably the easiest one is they tell you, hey, this is the fast mechanism, this is the slow step or the fast step, and it's always going to be the one labeled slow is your RDS, like the one we see on the screen here. Another way, again, you could determine which one is sort of the rate determining step was, I think, an example like we looked at earlier, like here, for example. Here, they didn't necessarily label each of the steps as fast or slow, Um, but they did give us the experimentally found rate law in the problem. And by going through sort of these elementary steps, we were able to write rate laws for each of the steps individually. And as we talked about, this is the only place where you can use the coefficients as the exponents in the rate law. Is when you're writing rate laws for elementary steps. So for elementary steps, you can actually use those coefficients as the exponents and write the rate law. And that, again, is the only place you could do that. Everything else, like we talked about previously, still stands. You do need to find them experimentally and stuff like that. But in sort of the process of looking at a mechanism, you could do that. And in this particular case, what we saw was that step number 1, I believe, had the same rate law as the one that was found experimentally. So even though they didn't tell us that, what that would mean is step number 1 in this mechanism would be the slow step and would be the RDS, or the rate determining step in this mechanism, which means in this particular mechanism, it is that first step that takes the longest, and then once that step's over, we would assume that the second step should occur relatively quickly along the way. Another sort of mechanism problem that we talked about was one such as this, and in this situation, we want to kind of determine whether or not this mechanism perhaps is a plausible mechanism to occur. And in this type of mechanism type problem, it's more like a proof. So you have to sort of figure out what the rate law is for that slow step, which we did. And usually in this type of mechanism problem, what you'll find is you will have a intermediate that's involved in that step or in that rate law when you write it. And we need to kind of compare apples to apples, which means we need to compare things in the overall reaction in terms of the rate law. And in this case, you need to do some substituting. And what we wanted to do here was to substitute out the intermediate so that we could then have a rate law that has everything just like it is in the overall reaction that's present, and then kind of compare and see if it match. And again, if it does match, it's a good one. If it doesn't, then it's obviously not the greatest there. Any questions on any of that stuff we talked about last time? All right, so I don't think you have this one, but since we have some time today, why not? Let's do one more of these sort of mechanism problems here just to make sure everybody's on the same page. So here we want to know, is this possible mechanism plausible? Is it a good mechanism? Is it a necessarily bad mechanism? The experimentally observed rate law was the rate is equal to K times H2 and O2, NO, for this reaction here. So this is a 3-step proposed mechanism. So why don't you take a few minutes here and kind of work through it, which again, you basically want to do is try to determine whether or not this is, for lack of a better word, a good mechanism or bad mechanism, basically. And you sort of has to prove it. So this is sort of what we talked about last time, kind of like a, here's the answer. You need to prove, is it right or wrong in doing that. So since we got some time this week here, not much going on, let's do one more just to make sure everybody's on the same page here. And so take a few minutes here and then we'll talk about it. So those are the steps. And again, I don't think this one was in your notes, so I just kind of wrote it up there. Okay, so let's take a look at this one. So again, remember that really when you're kind of looking at a mechanism, there's those two things that really needs to occur in order for it to be, again, it's oftentimes referred to as sort of a plausible mechanism for this reaction to occur, or if you just want to cut to the chase, there is a good or bad type mechanism. So the first thing is really you do need to add up all the steps, and once you add up all the steps, does it equal sort of the overall reaction that you're looking for? So in this particular problem, we are looking for this reaction here overall. If I didn't write it wrong, hopefully I did. All right. So what we want to do basically in this case, we actually have 3 steps here. So we're going to add up all 3 of these guys here. And when we do, again, things on opposite sides of the arrow can cancel. Things on the same side obviously stay. So in this particular case, the N2O2 will cancel. They're on opposite sides. One's on the left, one's on the right of the arrow. We also have N2O that will cancel as well. And I think that's it in terms of canceling. So overall on the left-hand side, we got 2NO plus 2 of the H2. Go to our right-hand side, which looks like 2 waters and an N2 in this particular case. So in comparison, what we get when we add up all these steps and cancel out everything along the way, we do see a overall reaction that does match the one that we're looking for. So far we're doing all right here in terms of this mechanism. You know, it is looking good so far. We also can see that the N2O2 does not appear in the overall reaction, which means that is an intermediate. We are N2O2. We also see that N2O is also canceled out and not found in the overall reaction, which would also imply that the N2O was also an intermediate. Any questions on just that part of it here? Now, a couple other important things, right, is what we know is that the rate law for the rate determining step should match the one that was found experimentally, which was also given to us over here. And we also know that the rate determining step is going to be the slow step in the mechanism. And in this particular case, that's pretty easy to find because this one right here is labeled slow. So this slow step here would be our rate determining step. That means that if we write the rate law for step number 2, we get that the rate equals K times H2 times N2O2. And again, we would want to take this rate law for our slow step and compare it to the one that was found experimentally. Problem, though, is as we talked about last time, we kind of want to compare apples to apples here. So we still have this intermediate that is present. So in order to sort of properly compare the rate law for that slow step to the one that's found experimentally, we do have to do some substitution here. And we do need to do some substitution by really using the other steps in the mechanism. So I'm just going to flip the page here. And if we look at the first step, step number 1, it is a reversible reaction, which means it has a forward direction and also has a reverse direction. So if we write the rate law for our forward direction, we would get that the rate for the forward, I'm just making an F, equals K times NO, and we would square it here. Again, the only place where we can sort of use those coefficients as the exponents. We could also write a rate law for the reverse reaction. So again, this is a reversible reaction that reaches equilibrium, which is, again, what that means. It's going to reach chemical equilibrium. So if we do it for the reverse reaction, what that means is our products will become our reactants. So we will get K times N2O2. We also have for step number 2, which is our slow step, we have the rate law that we just talked about. Just to recap our rate laws here, rate is equal to K H2 N2O2. We could write a rate law also for step number 3, although in this particular case, we may not need to use it. But if we did, we could write that the rate would equal K times H2 times N2O. So remember that the reason I say we may not even need to worry about this one is we're really interested in getting rid of this guy. And really the only other step where that appears is in the first step of the mechanism here. So we really could just use the first step to help us achieve that and sort of get rid of the intermediate. And as we talked about last time, when that reaction, which is a reversible reaction, reaches equilibrium, the rate of the forward reaction will equal the rate of the reverse reaction, which is basically what that means. And that means that we can set each of those things equal to each other. So taking step 1, we could set that forward reaction equal to the reverse reaction. And again, here we're looking to solve for N2O2, which means we essentially just need to bring K to the other side. These will cancel here. That will then give us that K times NO squared over K equals N2O2. This now is something that we can take and substitute into our slow step. And if we do that, now our RDS rate law will look like the rate equals K times H2 times K NO squared divided by K. Now, in this case, as we talked about before, all 3 of those Ks are the rate constant, which means it's a constant number, and they all should cancel except for 1. So essentially, they just become the rate constant. You should be left with 1. And if we kind of clean it up a little bit, we see that our rate determining step has a rate law that is equal to K times H2. Let's move something out of my way here. There we go. And NO2 NO squared. So based on the mechanism, this is the rate law that we should have based on this mechanism. So again, to determine if it is good or bad, we want to take the rate law that was found experimentally, which in this case is the rate law that was observed or experimentally found, K times H2 and NO. Because I forgot to write the squared part, so that's good. So this is the one that was found experimentally. This is the one over here that is based off of our mechanism, what it should be. And now in comparisons of those two, which were sort of apples to apples comparison here, we see that they actually do not match in this case. And they do not match, which means this is a, for lack of a better word, bad mechanism. Yeah. So again, the rate law for the slow step in this mechanism did not match the experimentally found rate law, and that would tell us that this is not a good mechanism. Again, if this happened to be NO squared and they did match, then like the ones we had previously, they would be a good mechanism in that case. Any questions on any of those steps, sort of what you're looking for? I would say, again, this would be a more kind of detailed mechanism type problem. Yeah. Any questions on that? Okay, so I just want to go over another one since, like I said, we do have time, so might as well do it just to make sure everybody's on the same page here. And now to officially finish up this chapter here, we're going to finish up talking about catalyst. And catalyst, as you may be aware of, is a substance that typically will increase the rate of a reaction. Again, a couple important things about catalyst that I think we mentioned earlier, but just a reminder, a catalyst is not a reactant. and it's not a product, and it does not get used up. So it doesn't get used up there in a chemical reaction. It's there at the end. It may get used a little bit along the way, but it can get regenerated as well. So for that to sort of be clear, a catalyst doesn't mean it just kind of sits there and really doesn't do anything. A catalyst can sort of, in certain cases, sort of get used, but then in the process or the mechanism of that particular reaction, that catalyst itself will then be sort of regenerated by the time the reaction is done. So that also does happen. Again, we sometimes think about it just kind of sitting there, is not really maybe doing much, but certain catalysts, depending on what they are, can sort of get involved in sort of the reaction part of it. But again, they get sort of regenerated by the time the reaction's over and they're still present there. So how does a catalyst work? How does it sort of do that? Well, a catalyst, for the most part, sort of a lack of a better sort of description, is it finds a sort of alternative path for everybody to come together in a much more sort of efficient manner than they would if they were just by themselves and trying to do it, kind of find each other by, just kind of floating around or whatever it may be. So for example, if you took some, a reaction you maybe did in like Chem 3, if you took Chem 3, very popular reaction that's done, some potassium chlorate, you heat it up, and you get a little KCl going on, and you get some oxygen gas that's going to be generated, and there's a lot of balancing involved there, probably, I imagine. Let's go with maybe a 2 there and a 2 there, and a 3 there would be good. So let's see, there's 6 oxygen, 6 looks good. 2 and 2, perfect. So maybe if you took Chem 3 at Saddleback, we do this experiment, you throw this in a test tube, you heat up the test tube, water comes out the test tube, hopefully. You have like a stopper on it with a tube that you connect. And I think this is the one you attach to the little green trays with the water that are filled with water, and it kind of gets filled up there. Now, if you do this reaction, for example, it actually does occur super slow. So if you heat this up, it occurs really, really slow. And you might not have witnessed that if you did that Chem 3 experiment, for example, because in addition to the potassium chlorate that was there, they oftentimes will put in there a catalyst, and that is MnO2. So this manganese 4 oxide, or in this case, a lot of times it's called manganese dioxide, different reasons. But this is a little black sort of powder that they put in there. And in the Chem 3 experiment, they actually pre-mix it in there for you. In every school I teach at, kids actually have to scoop that in to do this experiment. But by the addition of this MnO2, which is a catalyst, it really does facilitate this reaction happening a lot quicker. And I know it happens really slow because in that school where I teach, and the kids don't scoop enough of it in there, they're there all night waiting for the oxygen gas basically to develop, and it will never will because they typically don't put enough of it in there to sort of catalyze this reaction sort of correctly. So this is something that will sort of speed up that reaction, and catalyst could be just a place where it provides everybody kind of gravitating to allow everybody to come together a lot faster. But ultimately what it does in terms of, if you look at sort of the reaction, like the 2 diagrams that we see here, is it is able to basically usually speed up the reaction, because when we throw a catalyst in there, because it sort of has an alternative pathway, if you will, to get this reaction to occur. So the mechanism itself may be altered a little bit by the addition of the catalyst. So it may happen in maybe a different series of steps, or the rate determining step becomes sort of a faster step than it normally would occur if the catalyst wasn't present. But it typically will lower the activation energy by finding this sort of alternative path for this reaction to take place. And since this hill, which is our activation energy, basically determines how fast a reaction will occur. If we're doing the reaction on the left here, which is uncatalyzed, they got to go all the way up and over this hill, right, to get to the other side. While if we throw a catalyst in there, obviously much smaller hill basically to climb to get to the other side, and thus the reaction would occur a lot faster. So what we see is typically the activation energy will come down in a catalyzed reaction. That also will increase the K value, or the rate constant, right, which is basically your speed of the reaction, right? Rate constant increases, the speed of the reaction will increase as well. And that's a good measure of that. So we see activation energy go down, rate constant go up, reaction occurs a lot faster. Now, they again can sort of, catalysts can be a couple of different things, but ultimately, like I said, most of them will basically allow that activation energy to be lowered, and thus, sort of allowing the reaction to occur a lot faster. It's kind of like the old, say, cartoon, like I may have mentioned earlier, like the Roadrunner or whatever it is, right? And you got the big giant hill. So instead of going up and over the hill, the Roadrunner opens the door, right? Goes right through the middle of the hill to the other side, closes the door, Coyote hits the door, laps ensue, all that good stuff, right? But again, the Roadrunner could get to the other side because he just kind of went right through the mountain rather than up and over the mountain, which obviously would get him to the other side a lot quicker. So it's just a sort of an alternative path for these reactions to take place, and it helps them be better sort of kinetic wise for them to take place by finding sort of these alternative ways. And really what does sort of change a lot of times is those mechanisms, so those elementary steps that occur in sort of the natural way that these reactions would take place is sort of sped up because of the presence of this catalyst. Again, a reminder that, as we talked about many times, that if a reaction is spontaneous, again, doesn't mean that it occurs like super fast. There's a lot of spontaneous reactions that are super slow, and they can be sort of aided by adding a catalyst to it. Now, probably like I mentioned before as well, 99 times out of 100, if somebody mentions something about a catalyst, they're most likely talking about it in the sense of it speeding up a chemical reaction. It is possible that a catalyst can actually slow down a chemical reaction. And those, again, are sometimes referred to as a negative catalyst. Sort of, you want to think about it in like the nuclear chemistry sort of idea of that sort of approach. If you think about what we talked about in terms of a nuclear power plant, they have those control rods where the control rods basically take out the neutrons in those reactions, thus slowing the reaction down and kind of keeping it under control and stuff like that. So, just off the top of my head, that's sort of an example of sort of a negative sort of catalyst, something like that, where obviously if you needed something, it may take something out of the reaction sort of for a bit, and obviously keep the reaction occurring a lot slower. Now, there are different types of catalysts, and for example, some are heterogeneous catalysts. And heterogeneous, just like it means when we talk about heterogeneous mixtures, sort of different phases, you can see different layers. Same thing here with a heterogeneous catalyst. The reactants and the catalysts are in different phases. So a couple, three sort of examples of that is the Haber process for ammonia. So the formation of ammonia, nitrogen and hydrogen gas come together, is a spontaneous reaction. It is also a very slow reaction. If you wanted to do it for any type of commercial production or something like that, it takes a very, very long time for it to occur. So the addition of a catalyst like a solid state catalyst, as hydrogen gas, nitrogen gas, or gases, a solid state catalyst, something like iron metal, I think it was, allows those gas molecules basically to come to a central location. And because they come to that central location, it allows them really to come together a lot quicker, and thus increases the rate of that particular reaction. I think we'll see some pictures here in just a second. Also, the production of nitric acid is another one. Again, something like I think a platinum wire or something like that is used. Again, that solid platinum is obviously different than some of the gases involved when that reaction occurs. And then catalytic converters in our cars, we'll also see a picture of that, I think. And again, there's solid metals in there, transition metals and so forth, in the actual catalytic converter in your car. And as sort of the fumes come through the exhaust, which are gases, they come through, obviously they're in the gas state, these are in the solid state. So as they pass through there, it allows, you know, certain reactions basically to take place, which cuts down on obviously the emissions from your car. Now, there's also catalysts that are homogeneous, and homogeneous means basically the same throughout, just like in a mixture. And these are catalysts that are basically in the same phase as your reactants. So most commonly we see that with acid catalysts, base catalysts. And again, we see all these guys typically in reactions, for example, on top of, you know, the arrow there, right? So something like platinum's up there. Here you may see something like H+, which acts as an acid catalyst, sort of rich on top of the arrow. But obviously if it's an acid, right, an acid means basically it's able to produce H+ in a solution, which means it's in the same form as usually, say, another solution that's present, that's also there as well, floating around in the same solution. So everybody's floating around in a solution as ions. Obviously, as we talked about, ions are good to go in terms of reaction, no bonds that need to be broken. So that's going to help facilitate everybody sort of reacting a lot quicker. So this here is the Haber process. And again, you can see iron, some aluminum oxide, some potassium oxide sometimes used. And these are our hydrogen and nitrogen gas molecules flying around. In the absence of this solid catalyst, they got to fly around and eventually come into each other, connect with each other with the right amount of energy for this reaction to occur to make like NH3 over here, right? And this is like H2 and N2. Now, if you add something like this iron piece of metal here, what happens is both the oxygen gas and the nitrogen gas, for lack of a better word, gets like stuck on it. You know? So you got your nitrogen, your oxygen sort of gets stuck. When it gets stuck and sort of bound to it, it actually binds to this metal. And so doing so, what it does to both of these gases is it weakens their bonds, which is also good, right? If we want them to kind of break apart and come back together. So by sort of attaching to this catalyst, it also serves to sort of weaken the bonds between the nitrogen, the hydrogen, and the hydrogen. And as you can see over here, they essentially sort of, you know, all separate out into some hydrogen atoms, some nitrogen atoms. And now they're ready to sort of assemble a lot easier. You could kind of almost see these three guys coming in to assemble, you know, these three guys over here coming in to assemble, and they're able to assemble into NH3 in a lot quicker fashion than they would if that catalyst wasn't there. So in this particular case, sort of the catalyst does serve sort of two functions. Again, it's sort of a collection area where both gas molecules are sort of attracted to it. And then by the process of those gas molecules sort of temporarily binding to that metal, it also does weaken the bonds that are there, which will obviously promote everybody coming together a lot quicker, a lot more efficient than, again, if that catalyst was not present. This is our nitric acid with our platinum catalyst. Again, similar idea here. It's a multiple sort of step mechanism that occurs, but again, starts with some gases, some NH3 and some oxygen gas. A solid platinum, so again, a heterogeneous catalyst here, going to allow some production of NO and some water. Then that NO will also react with oxygen to produce NO2. That NO2 then will get hydrated. That is an acidic oxide. Yes, if you remember, we talked about that in the acid-base reaction. It actually will form both of these guys. Yeah. That's nitrous acid, and then our nitric acid, which is what we're interested in. And actually in the process here, what they typically will do is take some of that nitrous acid and heat it up. And what that will technically do is make some more nitric acid, which is the intended goal here. And it will also make some more NO, which is also a very good thing in that sort of secondary process that occurs, because when it makes more NO, that's like feeding the second step in this mechanism. You're actually making more reactants for the second step in the mechanism. And obviously this process will occur a lot quicker. You'll make more nitric acid in this process than if this catalyst wasn't there. Again, if this catalyst wasn't here, this sort of first step here would take a significant amount of time for them to sort of come together. So again, it helps speed up that reaction and the production there of nitric acid in this particular case. Here's our catalytic converter, and in our car we do have a catalytic converter, and probably most of you know that gas is a hydrocarbon, basically. That's why we call it, you know, 91 octane, right? 87 octane. Octane is an 8-carbon organic molecule that's basically nothing but carbons and hydrogens. And when we use our combustion engine and we burn basically gas, we do get a couple of byproducts. Sometimes we get what's known as it's obviously a combustion reaction, right? And when everything's working really well in a combustion reaction, you know that you produce CO2 and water, right? Now, if you have an incomplete combustion reaction, which also happens, you don't produce CO2 and water, you actually produce carbon monoxide and water. And carbon monoxide, not so good in the environment. Obviously, it's a pollutant, and we don't want that sort of carbon monoxide being produced. Not good for us either, obviously. So one part of your catalytic converter, there's usually 2 chambers here a lot of times. One chamber here, one chamber there, and upstream, downstream type of deal. And here we have, when it goes through here, are unburnt hydrocarbons, which will produce that carbon monoxide, will then be producing CO2 and water. So this catalyst will basically make the CO2 being produced from that carbon monoxide in a very efficient manner, so that when it goes out your tailpipe, it's CO2 and water, like in a traditional sort of combustion reaction. Now, the byproduct of doing this, and when you heat up in this process, because this is done obviously under very, very high temperatures, right? Engines run very hot, right? And everything through here is super hot. A byproduct of that is NO gets produced. And NO is also not a great thing, because I think we have it on our last slide there. NO and oxygen produces NO2, just like it does here in our nitric acid process. And the problem with NO2 production is it is definitely a pollutant. It is the brown, smelly, not so good gas product that comes out of that. So it's a sort of smog pollutant. It's a brown, like not so great gas that comes out. So the second chamber here actually takes care of those guys. So that sort of NO that's being produced as sort of a byproduct of the first reaction then is made into nitrogen gas and oxygen gas. Again, those are what we find in the atmosphere in abundance. So obviously it cuts down both on those emissions as it goes through your car there, right? And it cuts down on those unburned hydrocarbons, and basically those nitrogen oxide, monoxide, which again can produce that NO2 gas that we really don't want either. So it kind of helps catalyze that reaction as well. All right. And lastly, we also sometimes see sort of catalyst and enzyme reactions. Again, they sort of need to fit together in the active site, like any other reaction here. There's usually an active site where everything sort of needs to fit in. I remember when I took biology, they used to make you do like the triangles to make sure it fits in and all that kind of stuff. But, you know, you have your substrate, your enzyme, and obviously some reactions will occur a lot faster in the presence of certain enzymes, which technically will speed up a reaction in a sort of biology type way. Any questions on catalyst there? So that officially now wraps up Chem 1B. Congratulations. We are now out of topics to talk about. So we're just going to awkwardly stare at each other. Well, I'll just stare at the screen. You can stare back at me if you want for the next 5 days. No, I'm just kidding. Any questions on any of that stuff there? Okay. So since we have time now, what I'm going to probably do is maybe for the rest of the time today and maybe tomorrow as well and Wednesday, maybe we'll see how far we get. I'm just going to maybe, if I think it might be beneficial, I'm just going to maybe just start back at where we started at the beginning of the semester and just try to hit sort of the highlights of those chapters. So hopefully the stuff you still remember. I guess it's better than a normal semester where you have 16, 18 weeks. This has only been, what is it, 6 weeks? So, or 8 weeks, or whatever long is it, 8 weeks. So a lot of the stuff should still be relatively fresh to you. And we'll just kind of hit sort of the main points of some of those chapters. And again, that should hopefully help you as we go into the finals. So a reminder, we got one more exam tomorrow, which covers stuff, but I believe it should cover transition metals, complex ions, coordination compounds. Should also cover, I believe, the complex ion KF from chapter 16, and then obviously kinetics as well. So I believe it should cover all that stuff tomorrow. Then Wednesday, last day, and then Thursday we have the final happening as well. Yeah. Any questions on sort of the schedule coming up? Okay, so since we got like 20 minutes or so to go here, we'll just start maybe sort of a review, and again, I'll just try to hit sort of the important parts. I guess they're all important, but just to remind you again, hopefully it should be pretty review as well. Yeah, so we're going to do everything kind of the same as we've been doing. So tomorrow we'll have a little lecture before the exam, and again, it will at this point obviously be some review. So we'll do just a little bit of review. We'll take a break like we normally do. We'll cut off a little bit early in terms of the lecture part. We'll take the exam during lab like we've been doing. So tomorrow during lab, we'll take exam 4. On Wednesday, like I said, we'll be kind of doing the review and all that kind of stuff. And then on Thursday, it'll be kind of open study type of time. And then we'll take the final during lab as well. Okay, I think. Yeah, so if you have any kind of specific questions about some stuff, you can ask during probably lab time this week. Probably be a good time today as well. So I think what I'm going to do is try to stick with the reviewing aspect here during just lecture time. And then lab time will be a little bit more open. If you have some more specific type questions, you could ask. And then probably Wednesday during lab time, we could get into specific questions for sure. But that's probably how it'll sort of go. So I just want to kind of go through the chapters here, maybe during lecture time today, tomorrow, and Wednesday. And that should probably be enough time, hopefully, to cover all the topics again. And then again, lab will probably use this week more of a, if you got a specific question, you could chat me the question or whatever it may be, and I'll be happy to answer those type of things. So just a reminder, tomorrow's exam should be the transition metal chapter. I'm sorry, I'm running. I don't remember what number that is. I want to say 21. Seems like it should be transition metals, if I'm not mistaken, right? And I believe it should be the chapter 16 part, which is complex ions, which is the last section. And again, I believe it should be kinetics as well. So I think it should be those 3. So I guess 2 in a section, basically. Yeah. Okay, so give me a second to kind of get something to write on, and then we will we'll get on that there. Let's see here. Okay, so again, you guys can all see it. It's correct size and everything, I hope. Yes. Okay, so we're going to then start at the beginning, I suppose. And for us, the beginning was chapter 13. So chapter 13 was chemical equilibrium. And so chemical equilibrium, as hopefully you should be familiar with, right, as we talked about many, many times here throughout the semester, involves a certain type of reaction, which is a reversible reaction, where essentially when we talk about equilibrium, as we've talked about, it means that the rate of that forward reaction will equal the rate of the reverse reaction. And that's important because, as we talked about, we're not talking about everybody ending up with the same amount, so same concentration on each side. It just means, as we just mentioned sort of in the kinetics chapter, as fast as they go to the product side, they will just as quick go back to the reactant side. So essentially, as we spoke about, what it will happen is wherever everybody is at that particular moment, when it reaches chemical equilibrium, means that they will essentially be locked into it, into their concentrations, into their pressures, because just as quick as they sort of lose some, they gain it back because the rate of the forward and reverse basically equals each other. And we saw obviously the number one thing for this semester, which was our equilibrium constant, right? Which is obviously the concentration of our products divided by the concentration of our reactants. And as we've talked about, obviously, we do use the coefficients here as our exponents when we do that, not to be confused with the rate law there. Actually put something there, so I actually should use it. Where we do not use that, we have to find them experimentally, but here, again, we can go right into that expression and basically do that. And we saw that, the value of K, and in this particular case, this is what is sometimes referred to as Kc when we do concentrations or molarities. The value of K gives us some information about what is going on in that reaction when we reach equilibrium. So obviously, if we have a large value of K, that obviously means that we have mainly products, right? When we reach equilibrium. And that's because, just mathematically speaking, if we take a big number on top, which is our products, divided by a small number on the bottom, we get a large value for K. And vice versa, if we have a small value of K, it means when we reach equilibrium, we should mainly have reactants involved for the same sort of mathematical reason. If we have a small number on top divided by a larger number on the bottom, which would be our reactants, we will get a small value for K. And remember that when we talk about large or small, one is sort of the number that we consider large, or above one is large, below one is considered small. So that's the importance there. Now, when we talk about sort of Kc and so forth, that has to do with the concentrations of everybody, but some reactions do involve gases. And when we do have guys that involve gases, we could write a similar equilibrium expression, which deals with pressures, right? Because gases deal with pressures, as we talked about. And it's basically done the same way. We're going to take our products over our reactants, but here we're going to be looking at our partial pressures. So for the example up on top, it would be the partial pressure. We would still square it of C times the partial pressure squared of D divided by the partial pressure squared of A and the partial pressure cubed of B in this particular case. Now, as we talked about, Kc and Kp do not necessarily equal each other, so they don't equal each other, but they do give us really sort of the same information in terms of when we reach equilibrium, what we would expect to be their products or reactants. So if we had a large value for Kp, that would mean that we would mainly have a lot of products at equilibrium, and most likely we would also have a lot of gas molecules at equilibrium, causing the pressure to occur. If we had a small value of K, P, that would mean we'd mainly have reactants at equilibrium, and again, more probably gas molecules on the reactant side, and thus also causing most of the pressure associated with it. Now, sometimes depending on sort of the information given to you, as we talked about, you sometimes need to go from Kp to Kc or Kc to Kp. And we did see a formula that allows you to go from one to the other. And to sort of tie those two together, we had that the Kp equals the Kc times RT delta N. And a couple of things that we talked about in this one, obviously our Kp is our equilibrium constant for pressure. Kc is our one for concentration. R here is our gas constant that we use for gas laws. So that's the 0.08206 number. T here is temperature that does need to be in Kelvin. And remember that delta N is the change in the number of moles of gas molecules. And that is delta N would be N of our products minus N of our reactants. And again, it's important to make sure that you actually do products minus reactants, because you may get a negative number like we talked about there. And if you do get a negative number, mathematically speaking, you need to take 1 over that. And that's going to be important if you just decide, oh, the difference is just 1. So again, that was the part where we talked about is really important in terms of the N, that you don't just ignore the negative part of it, because you will get a wrong number. Yes, so in terms of the question is a small value of K less than 1? Yeah, so anything technically speaking less than 1 is considered a small value of K, and that is usually your guys that have, you know, some type of negative exponent that's there. Anything typically above 1 is considered large. Now, there obviously is a variety of sort of numbers in terms of that, and we've seen different ones along the way. So for example, when we saw our KSP values, those are typically guys with very, very small K values, like to the minus 32, minus 23, super small values, right? And there's also ones that are extremely large, like what we had with our KF values. Those are guys that have like times 10 to the 30, times 10 to the 17, 18, so really large values of Ks. And obviously there's ones that sort of run in between those gamuts, but just to sort of illustrate, they can't go to sort of, I don't want to say extremes, but sort of like that. Again, we saw that very much happen with our KSPs, which were super small values that they're, almost pretty much going to stay on the reactant side. And that's where we saw things that were typically insoluble, right? So that's why they're so small. While we saw with our complex ion formation, those values are really large, which means that's why complex ions are really favored, because of that really large value of K that's associated with that. Other questions on that? Now, we also talked about that sometimes you do need to manipulate K values, and you do need to, in some cases, add together certain reactions to sort of build an overall reaction. And that does have sort of an effect on a K value, depending on sort of what you do to it. So for example, if we had 2A plus 3B goes to 2C, and the K value here is, we'll just say it's 5, right? And if we decide, well, we need this reaction reversed, right? When we reverse this reaction, we would have 2C goes to 2A plus 3B. Now, what happens to the K value, as we talked about, we could really see if we just look at the expression, this would be C squared over A squared and B cubed. The K value for this one would be A squared B cubed divided by C squared. Now, the difference between those two is they are the inverse of each other, right? The 1 over. So what we do is, if this is K1, for K2 in this case, we would take 1 over the K value here. And in this particular case, if you got the number, it would be 0.2 would be the K value for this guy. So again, that's different than what we do with a lot of things. Remember, in like delta H's, you know, those kind of things, if we reverse the reaction, we simply just change the sign. But it is different here with equilibrium. If we reverse the reaction, we do need to actually take the inverse of the K value, 1 over the K value, to give us the proper one. Remember that when we do see a K value written, it is specific for the reaction exactly how it's written for those at that temperature, right? As we talked about, the only thing that really affects the actual value of K is if you change the temperature. But if you keep the temperature the same, regardless of how much reactants or products you may start with in different sort of reactions, long as you keep the temperature the same, the proportion of reactants to products will always end up being a constant value. Again, no matter if you started in, say, the reaction on the left there with 2 of A and 4 of B, and the next time you did 3 of A and 4 of B, you will still come to that same proportion and have the same value. Other sort of manipulations that we talked about in terms of equations and K values is sometimes we may have a reaction that looks, again, like this. Let's say the K is 2. And maybe we don't need just 1 of everybody here, but we need, say, 2 of everybody here. So we multiply everybody by 2. Again, different. I guess I shouldn't have done it that way, huh? I guess we'll do, hang on a sec, let's just rewrite it so we can see it. Get rid of that guy, and that guy. There you go. So let's say we did need 2 of everybody there. If we went through and multiplied everybody by 2, what that does to the K value is we need to then square it. So the K value in this case would be 4. And again, it's the same thing. You see it with the equilibrium expression, product over reactants. And if we wrote it for our guy where we went through with 2's, basically the only thing we did is, if you look at the difference, in this particular case, we squared everything. So we would square the K value. Again, if we multiply by a common number of 3, we would cube everybody in terms of the K value. So also very different than, say, delta H's and stuff like that, where you multiply by 2 or whatever it is. In this case, you do need to square it. Also the same if you're going the opposite direction. So if you started, say, with the 2 and you actually needed the 1 of everybody, in that particular case there, you are going to actually take the square root in that case. So if you go from right to left on the screen, what's going to happen is we basically took the square root of everybody on the right and got to what's on the left. And in terms of the K value, what that will do is, again, you would take the square root of the K value. So you take the square root of 4, you end up with 2 in this example, and that's what happens. Same idea as well, if you started, say, with 3's all the way across and you need to divide by 3, you would take the cube root of it and so forth. So if you have to multiply by a common number, you essentially take the K value to that common number. So if you multiply by a common number, you take the K to that common number. And if you have to divide a reaction by a common number, you take the root of that common number, whatever it may be. So again, in this example, we divided by 2, so we took the square root. Again, if you divided by 3, you would take the cube root of it. Any questions on that so far? Then obviously, a couple other things that we talked about that were important was the idea of Q. Q is the reaction quotient. And that also is found by pretty much doing the exact same calculation as K, is the concentration of products divided by the concentration of reactants. And we can use Q and K to determine whether or not a reaction is going, not to be spontaneous now, we can use it to determine whether or not the reaction is at equilibrium. And if it's not at equilibrium, what it will tell us which way it needs to go to reach equilibrium. So if we calculate Q and it's greater than the K value, that means it's not at equilibrium. And it also means that in order to reach equilibrium, we need more reactants to make. So it has to go to the left here to make more reactants to reach equilibrium. We also saw that if you calculate a Q and it does equal K, it means that it is actually at equilibrium at that point. And if you calculate Q and it's less than K, it means it's not at equilibrium. And to reach equilibrium, it needs to go to the product side to reach equilibrium. And again, Q is calculated the exact same way as K. Again, it's just initial conditions in this case, not sure you're at equilibrium, so it helps you determine if you are there or not. We also talked about that if we wanted to obviously calculate equilibrium concentrations, that is everybody's favorite calculation, right? Which is our ICE table, right? And I would hope at this point you know how to do ICE tables. If not, you do have a couple of days to learn, I suppose, but I'm not sure what you've been doing for the rest of the time. But, you know, again, just a quick reminder, you typically will have your molarity here of your initial, and if you're not given anything for your product side, you could assume 0. Again, minus 2x, plus 3x, and again at equilibrium, initial minus 2x, initial minus 2x, my made up one, and 3x. The goal here is to solve for x. Again, a reminder that there's a few different ways we talked about you could solve for x. You may have something that's a perfect square. This obviously goes into the equilibrium expression, and you solve for x. But again, a couple of different ways. Could have a kind of a perfect square to do that, right? So you can square root both sides. You may have to use the quadratic, which we've used hopefully many times this semester, which again is our b squared minus 4ac divided by 2a. Remember that when you do use their quadratic, you get 2x values. One will not make sense, one will make sense. The one that will not make sense, again, is your one that gives you a negative concentration or like a negative pressure at equilibrium when you put it back in. And lastly, we can make an assumption, right? And we could assume that x is equal to 0. Remember that you could make x is equal to 0 when your k value is small. And that again means that we can get rid of all the x's except for really the x by itself. So when we talk about assuming that x is equal to 0, as we talked about many times, it is the ones where we subtract x from something or maybe add x to something. Those are the ones that we zero out. Remember, we also do need to check it, and that is our 5% rule that we've been using in this class, which means that the x value that you get, you then should divide it by the molarity you're going to subtract it from, times it by 100, and if it's 5% or less, you're all good. You could assume that the assumption is okay. If it's greater than 5%, that means you do need to solve it some other way. And again, for our class, that probably means quadratic. As we also talked about in those problems, if you don't want to even bother with the assumption part of it, you could definitely always go straight into the quadratic and solve it that way, and everything will be okay in that sense. All right, so obviously once you get the x, you go back into the equilibrium and solve that. I would hope at this point you know how to do an ICE table. Let's talk a little bit about the last thing, I think, in chapter 13, which was Le Chatelier's principle. And Le Chatelier's principle is the idea where we do have a system at equilibrium. And this is a system that's really happy. It's at equilibrium, which again means the rate of the forward reaction will equal the rate of the reverse reaction. But then you do something to it and you add a stress to the system. And when you add that stress to the system, it really messes up the equilibrium. And when it messes up the equilibrium, it causes it to no longer be basically, going back and forth at the same rate. So what I will do actually is we'll stop here, and then we'll just do a little bit more reviewing. Hopefully this was beneficial for you, I hope, so far. So we'll do just a little bit more. We'll save some, obviously, for the rest of the week. And then, like I said, for the rest of the time, so I don't keep going and just run way over. For the rest of the time in lab there, it'll be just, again, kind of an open study. You got a lot to study for and stuff like that. And you can ask some more specific questions or type me more specific questions if you want. So I'll tell you what we're going to do. We'll take our normal kind of 10-minute break here. We'll go to lab, and then I may just continue on, maybe just get into a little bit of chapter 14, and we'll stop there. And then, like I said, the rest of the time will sort of be for that. Any questions on any of that stuff so far? Okay, so let's take a break. We'll see you about 3. We'll do a little bit of reviewing, kind of keep it going. And then that'll be it for today, I think. Yeah. All right. So I'll see everybody about 3-ish. Make sure you put here if you haven't done so.